Hello and good time of day to you. I felt like a short break from ZX Spectrums, and so instead I'm going to have a go at repairing this Hitachi HA-4700 amplifier. It dates from the early 1980s, and all I've been told about it is that when it's switched on, the front panel lights light up as expected, but no matter which input is used or how the controls are adjusted, there is only deathly silence from the loudspeakers. Fortunately, it was easy to find the service manual online, and it's reasonably comprehensive. It includes a description of how to disassemble the amplifier, a full circuit diagram, a PCB layout diagram, a description of how to set up the amplifier, a complete parts list, and a description of the operation of some of the circuits. Here's a block diagram, the upper one here. There's nothing particularly unusual about that, it's fairly standard for this type of amplifier. But there's one thing that is a little bit unusual, and that is that this amplifier uses something that Hitachi calls a superlinear circuit. And there's a brief description of its operation in the service manual here. So far as I can tell, it's a method of dynamically adjusting the bias of the output transistors so that neither is ever completely turned off, and the aim of that is to allow the negative feedback to more effectively reduce crossover distortion. Whether or not it works well remains to be seen. Here is the complete circuit diagram, and I thought it would be helpful for me to have a good look at it before delving inside. It appears as if there were several different options for the mains input and transformer, and probably for different markets, and I believe this unit is arranged like this block. It certainly contains a pair of transformers, and they're connected to act as if they were a single transformer with a center tapped secondary. Over here is some general power supply circuitry. There's a bridge rectifier, some reservoir capacitors, and this looks rather like a voltage regulator circuit. Up here is the phono input preamplifier, and this section here contains the various input switching and tone controls, volume control, and general purpose preamplifier, leaving this section here, which is the power amplifier. Here's a close-up of the power supply and power amplifier sections. Helpfully, a number of voltages are labelled at various points, although some of them are quite difficult to read, but that should give me a starting point for some tests to make. For example, I notice here that the main power supply rails are labelled plus 49 volts and minus 49.2, which seems surprisingly precise given that it's an unregulated supply at this point. This regulator here appears to produce a 12 volt and a minus 12 volt rail, though I've noticed something a little bit strange that perhaps is a mistake in the diagram, and that's that this point here is labelled 23.8 volts, then quite reasonably on the other side of this resistor it's labelled 12.2 volts, and that I imagine is due to the operation of this Zener diode here. However, this connection here goes off to label B, and I notice that on the complete diagram, point B is up here, and this is labelled 12 volts 55 milliamps, so that's slightly strange. I think I will investigate that to see what's going on, although I don't think that's going to be anything to do with the fault this device has got. Let's zoom in a bit on the power amplifier section and see whether I can at least get a vague idea of how this works. I know that the audio signal arrives from the preamplifier stages along this link here and comes to one input of this differential pair. The other input of this pair is the negative feedback, which is taken from the output point of the amplifier. Then, perhaps slightly unusually, a differential signal is taken off from here to another differential pair, and I assume that this section of the circuit here is responsible for most of the voltage gain. According to the description in the service manual, these transistors here are responsible for the superlinear circuit, and carry out the dynamic bias adjustments. The output is by a simple pair of complementary power transistors, and there doesn't seem to be anything particularly unusual about that. There are a couple of things that are possibly a little bit unusual, and that is, I note that there are 3 thermistors in this circuit, and I think they are the only means of temperature compensation in the bias circuit. Also, these resistors that are shown in black, so one here, some more here, etc., are fusible resistors. So those are things that certainly I should make some tests of, because they could be causing the fault. Over here is what looks like a custom IC that performs various monitoring functions, and the labels on the blocks inside give some clue as to what they might be. It looks as if this transistor here monitors the voltage across this 0.22 ohm resistor, and therefore the current flowing through it, and if that current should become too high, then it looks as if this input here that's labelled overload detect gets pulled high by this transistor. There's also another block here that's labelled neutral point potential detect, and that's connected directly to the output, and my suspicion at this point is that that monitors for an excessive DC offset on the amplifier's output. This device then controls a relay that is used to switch the signal before it reaches the terminals on the rear of the amplifier. So a fault in this monitoring IC, or some fault in here that triggers this to detect a fault, could well be the cause of our problem. So one thing to look out for is to see whether or not the relay is switched on when the amplifier is powered up. As I imagine that at some point fairly soon I'll want to plug this in and turn it on, I first want to check the rating of the fuse inside the mains plug. You'll certainly understand my reason for this if you've ever accidentally shorted the main supply inside a piece of equipment that has a 13 amp fuse instead of, say, a 1 or 2 or 3 amp fuse, and I'm quite pleased to see here that this is a 3 amp fuse. And while I'm in here, I might as well check its continuity and make sure it's working properly. It appears the fuse is good, so we're off to a good start there. It might also be an idea, while I'm here, to check the resistance between the live and neutral terminals of the plug. That should give me some guide as to whether the on-off switch is functioning and whether the transformer primaries are intact. So at the moment it's reading open circuit. The on-off switch on the front panel is in the off position, so I'll turn that on. And 14.4 ohms, so that suggests that at least one of the transformers has an intact primary. According to the circuit diagram, they're both wired to the mains input, so I wouldn't be able to tell whether or not one of them is faulty, but again, that's a promising start. Now I'm going to have a look inside. When I first received this, I took the cover off, had a quick look, and cleaned out a lot of the dust and fluff, so hopefully today's experience won't be too messy. I've removed the 3 screws on each side, and so the case should just slide off. So let's see now whether I can relate what's in here to the circuit diagram. It appears as if some of the circuits relating to the front panel switching are not too surprisingly mounted along the front here, and these 2 boards are boards that I didn't mention earlier but are shown on the circuit diagram, and they drive the LED power meter display on the front. Clearly the 2 mains transformers here, the bridge rectifier, the main reservoir capacitors, these great big heat sinks must be for the output transistors. I can see that the mains comes in through this wire here and is soldered onto these terminals. I always wonder quite how something with a mains connection like this inside a metal case can be considered double insulated, but it is, and even a brand new piece of equipment like this wouldn't be very different. There'd probably just be some extra insulation over these connections so that I wouldn't easily be able to stick my fingers in there and be electrocuted if I took the cover off with the power on, but quite likely the mains will still pass on to the circuit board. There are a pair of fuses in here, and I'm going to go back to the circuit diagram to see where those fuses should be. And those fuses are on the main side of the transformers. So given that I measured some resistance between the live and neutral pins of the plug, at least one of those fuses must be intact. So let's make a quick check of that and confirm they are both working. I'll set the meter to its continuity test mode again. And both fuses test good. I've had a closer look and identified all the main areas of circuitry. Down here are the two voltage regulators that generate the plus and minus 12 volts. Each one of these strips is a power amplifier, one for each channel. Helpfully, the component identifiers in this area of the circuit are identical between the two channels, but have an R or an L suffix to identify which channel they're associated with. Over here is the phono preamplifier stage and a slightly interesting cable operated switch to select between an input for a moving magnet or moving coil cartridge. I was slightly confused at first by this odd plastic coated thing that runs the length in between the two power amplifier sections, but it's described in the service manual, and it's simply a fairly clever way to carry the different power supply rails to all the areas of the circuits where it's needed, and I imagine that makes laying out a single-sided circuit board like this quite a lot easier. By checking the part numbers, it appears that the resistors that are mounted standing up from the board, like these ones here, or the light colour blue ones, are the fusible resistors, so probably at some point I will need to check those. I also can see that a few of the transistors have got what appears to be heat-proof sleeving slid over the top of them. I'm not too sure what that's for. I assume perhaps to protect them from any hot components nearby, but only some of them have got this covering and other transistors right next to them haven't, so that's a little bit of a puzzle. Hidden away at the back here, down between the speaker terminals and the output inductors for each channel, is this relay, and that clearly must be the relay that switches the output to the speakers on and off, and is the thing controlled by the custom monitor IC, although I can't see anything that looks like an integrated circuit package on the board down there, so I'm not sure where that is. Before I try switching this amplifier on, I want to make a couple of measurements that will hopefully convince me that nothing should explode or burst into flames, and that's just to check for any short circuits between the power supply rails. I've connected one lead of this multimeter, which is set up to measure resistance, to the negative side of one of the speaker terminals, which is connected to the 0 volt rail and also connected to the chassis, which I can show if I press the other probe against the metalwork back there. I can access the power supply rails in several places. First option came to mind was at the bridge rectifier, but it's a bit difficult to get the probes in under there. So then I realised that of course they're both present at the collectors of the output transistors. The positive rail should be present at the NPN output transistor and the negative rail at the collector of the PNP output transistor. And thankfully and helpfully, the terminals of the output transistors are labelled clearly on the circuit board. So here's the connection to the collector of one of them, and the reading is gradually increasing. That's going to be as various capacitors charge up from the supply provided by the meter, but it's a relatively high reading, so I don't think there's a short circuit there. I will try the same thing with the other transistor for that channel, and the result is almost identical. So there doesn't seem to be a 0 volt, a short between either power supply lines and 0 volts. I will do one final check, which is to make sure there's not a short between the two power supply rails. So I'll put the probes across the collectors of the two output transistors for one of the channels. The amplifier is connected to the mains via a residual current protection device that should turn the power off if more than 10 milliamps leaks to earth. So I'll press the magic button. Some of the front panel lights have come on. The selector switches seem to work as expected. When I turned the power on, I listened very carefully to see whether I could hear the speaker switching relay click, and I heard no click at all, so either it's very quiet or it hasn't operated. First up, I'm going to check the main power supply voltages. I've already connected the common terminal of this meter to the 0 volt line, and I'm going to find the two power supply rails at the collectors of the output transistors like I did before, and the diagram says they should be around about plus or minus 49 volts. Minus 51.5, I think that's close enough to 49, and the other one just over 51 volts, so I don't think there's a problem there. I'm now going to check the voltages at the emitters of the two transistors involved in the voltage regulator, and the circuit diagram says that those should be at about plus or minus 23.8 volts. So let me try to connect the probe to those. I think both of those are close enough too, so there's not a problem there. I'm also going to check the plus or minus 12 volt lines as generated by a pair of Zener diodes, but I'll need to move the camera out of the way to get to those. With the camera out of the way, I located the two Zener diodes that are responsible for the plus and minus 12 volt supply. They're hidden down underneath here, and I measured more or less plus and minus 12 volts, so I think they're both working correctly. Noticed a few other things while I was looking around the circuit board. After the amplifier had been turned on for a minute or two, this pair of transistors here had become quite hot, whereas the equivalent two in the other channel here were completely cold still. You might remember that earlier, when we looked at the circuit diagram, I wondered about this power supply connection to the phono preamplifier, which is labelled here 12 volts 55 milliamps, but here appears to connect to the 23 point something volt supply. Well, I found that IC on the board over here, and I've measured that supply connection, and it is the 23.8 volt supply, so this label is incorrect. I identified these resistors here, these large 0.22 ohm power resistors, as being the emitter resistors in the output stage, and this point and this point are connected together at the output of that channel. And so I thought it would be interesting to measure and see whether there's a voltage present there, as it's normal for there to be a small offset voltage at that point, but it should only be small if everything's working and adjusted correctly. So I will turn the power on again, and check the left hand channel, and at the channel output it's about minus 158 millivolts, which is probably not unreasonable and is within the range that could be adjusted out with the controls. Yet if I check this one, it's at 27 volts, which is clearly completely wrong. It shouldn't be like that at all. That's a little bit strange. I thought it might be then an idea to measure the voltage across each of these resistors to see whether there's any current flowing through the output devices. So if I do that in the left hand channel, I measure around about 20 millivolts, and the same again in the other emitter resistor. They ought to be the same because there can't be any current flowing out to anywhere else at their junction. If I try the same in the other channel, absolutely zero, so there is no current whatsoever flowing through the emitter resistors in the other channel. I'll turn the power off now. I located one more thing. I've been wondering where the monitor IC is, IC 901, and that's the device that's supposed to control the relay that switches the speaker terminals on and off, and I found that is installed on the rear of the board. Down here I can just see part of it through this hole. It's another day, and before I get too carried away with taking dozens of voltage measurements inside this thing, I thought it would be a good idea to connect up an oscilloscope and make sure that the DC voltages being indicated by the multimeter really are that, and not the result of an AC waveform, say an oscillation or large amount of ripple. So I've done that, and that didn't seem to be the case, so I think I can trust the multimeter. And while I had the oscilloscope connected up, I thought it would also be interesting to try feeding a signal into the amplifier and see whether it makes its way through to the output in any way. So I've got a signal generator set up to inject a 1 kHz sine wave into both channels of the amplifier, and I've got the oscilloscope probe connected up to the output point of the left hand channel. I've turned the amplifier on, and now I'll gradually increase the volume control from its minimum setting. The signal begins to clip at close to 100 volts peak to peak, which is what I'd expect given the power supply rails are about plus or minus 51 volts. So it looks as if the left hand channel may be working correctly. Now I'll turn the volume down and move the oscilloscope probe over to the output point of the right hand channel. And straight away I can see the offset of about 27 volts that I measured before with the multimeter. And now I'll turn the volume up again and see what happens this time. I'll adjust the trigger level. If I turn the volume up, I can see the waveform clips against the positive power supply rail, so it looks as if at least that particular output transistor is working. And the main problem here clearly seems to be an offset in this circuit, so I suspect the other output transistor never even gets a chance to turn on, and that's why we can't see the negative going portion of the waveform. After the amplifier had been on for a while, I noticed that perhaps the left-hand channel isn't as healthy as it first seemed. The oscilloscope is showing the output of that channel again now, and it looks alright. However, if I turn the volume control down to lower the level of the output and adjust the oscilloscope's vertical scale, then it becomes clear that something's not quite right, and that obviously looks like an oscillation superimposed on the 1 kHz signal. So if I adjust the time base and zoom in on that, there it is, another unexpected signal at around about 1.5 volts peak to peak. And I'll turn on the cursors and measure the frequency. Somewhere around 9.5 megahertz, so I don't think that should be there, and it probably indicates some so far unnoticed fault in the left-hand channel amplifier stage. I've been busy with my multimeter. First of all, I measured the voltage at every point where I could find and read a value marked on the circuit diagram. For the left-hand channel, the values I read were reasonably close to the expected ones. Certainly none were out by as much as an order of magnitude. But in the right-hand channel, the dreaded value of 26 or 27 volts turned up at almost every point. One of the difficulties in pinpointing a fault in a circuit like this, where the whole thing is enclosed in a loop of negative feedback, is that the effects of a fault at one point are propagated around the circuit, and it can be difficult to identify the origin of the error. I then went on and used the multimeter's diode test mode and checked every transistor and diode junction in both channels. I had to refer to the circuit diagram because I was doing it with the devices in circuit, but I didn't find any particularly unexpected results, and certainly didn't identify any junctions that had failed short circuit. Finally, I measured the resistance of every one of the fusible resistors while they're in circuit. So again, that has to be done carefully with reference to the circuit diagram, but it shouldn't ever be possible to read a value that's higher than the actual value, and here are the values I recorded. Many of the resistances have drifted significantly from what were hopefully their original values. I don't know whether this is simply due to old age, or because this amplifier has been subjected to some particular abuse. Two results stand out in particular, and therefore R713 and R714 in the right-hand channel. The value of these resistors has changed enormously, and surely this must disrupt correct operation of the circuit. I'm using these leads to attach 100 ohm resistors in parallel with R713 and R714. These were the two whose value was most dramatically incorrect. The oscilloscope is attached to the output of this channel, so now I'll try switching the amplifier on again. I can see from the oscilloscope that the large DC offset on the output has vanished, and I doubt you heard that, but I just heard the relay click. This is the output of the right hand channel, and I'm slowly turning the volume control up. And the signal clips at close to 100 volts peak to peak, so that's a very good sign. It looks as if this channel is at least mostly working now. Let's see whether there's any high frequency oscillation present like there was in the left hand channel. It looks rather as if there is. It's at about 2 volts peak to peak. But at a slightly lower frequency, perhaps close to 8 MHz. My next step will be to obtain replacements for all of the fusible resistors. I think I should replace even the ones that seem to have retained their correct value, as it's clear the type used in this amplifier are prone to drifting or they've been damaged by some unknown event. The service manual says fusible resistors should be used to protect the semiconductors in the event of a fault, so I will try to use similar types, but I don't think it'll matter too much if I have to replace some with ordinary resistors.